Sorry you missed that. Okay. Here you go.
Okay, so implicit differentiation is how to take the derivative of stuff that you can't take the derivative of otherwise, because the x's and the y's are linked together in such a way that I can't solve for y. So everything we've done so far has already been like y equals whatever. And everything was x's, so you took a derivative in terms of x. But the problem now is a function like this, it's actually not a function, it's a relation. And just for your learning satisfaction, it looks like this.
Oh, that's not a function.
I said it's a relation.
You literally just said that.
Erase it.
Right?
Is that the same? Is that the same slope on either, like going down or not?
Not a line.
No, it's not constant. No, I mean it's loopy. It's loopy. So it looks like this. And you know, this is one of those graphs that like you couldn't use your calculator to graph because you couldn't put it into y equals. You couldn't solve it for y and put it in. So you'd be really stuck on how to graph this unless you knew something about volumes, I guess. But to take the derivative of this, you just need a different technique. It's called implicit differentiation. It's called implicit because when you can solve a function for y, it's called an explicit form. And when you can't, it's called an implicit form. So, to take this derivative, the rules still work as is, but every time you take a derivative of an x, you're going to have to chain on a dx dx. I guess it's in a second. And every time I take a derivative of a y, I'm going to have to chain on a dy dx.
Stupid.
It's something that we've done all along, but we just haven't had to say it because it hasn't mattered. When we took derivatives of like y equals 2x, we actually said y prime equaled 2 times dx dx. We actually did chain on the derivative of x, but dx dx is just 1, so it didn't matter, so we didn't talk about it. But now that we're going to be taking derivatives of kind of two separate variables within one problem, when I take the derivative of y, I'm going to chain on a dy dx, which is not equal to 1. It's different. So what the dy dx and dx dx mean is, this just means the derivative of x with respect to x, and this means the derivative of y with respect to x. So the reason why the derivative of x with respect to x is 1, it's the same thing over the same thing, and then this is a little bit different. Now, just for our sake, dy dx, I'm going to write that as y prime because it's a little easier. And dx dx is just 1. So I don't actually ever have to use the dx dx. But you should know that it's there. We just don't write it because it's just 1. So, the time that I'm going to use it is a problem like this. Let me go through one and then see if it makes sense.
Minus 9x
okay.
equals 0.
The derivative of x to the third is 3x squared dx dx. But I don't care about the dx dx. I've had that all this time and I just haven't told you about it because it's kind of confusing. And you don't need it. But what I do need in the next term is the derivative of y to the third is 3y squared times dy dx. I'm technically chaining on the derivative of y. Instead of writing it as dy dx, I'm going to write it as y prime. Be careful you don't trick yourself into thinking you wrote y to the first, because it's not. It's y prime, it's a derivative. I just find it gets annoying to write dy dx all the time and dx dx all the time. So derivative of x to the third is here. Derivative of y to the third is here, minus. I'm going to put this in parentheses because it's going to get kind of tricky, because what do you think I need to use for that derivative? I need product rule. Because I have 9x and a y, and x and y are two different things, two different variables, I need product rule. So I'm going to group this up into 9x times y and use product rule. Yeah.
Can you group both x and y?
I could actually bring the 9 out here and group it up x times y. Want to do that instead?
Yeah.
Okay. Okay, let's bring the 9 out and make it x times y. So between x and y, I'm going to use a product rule. So product rule says it's the first term times the derivative of the second. Well, what's the derivative of y?
Y prime.
Y prime. It's 1, y prime. Plus the second term times the derivative of the first, which is 1. dx dx, but I don't care. I don't care about the x prime. It's just 1. Equals derivative of 0 is 0. So I'm just taking the derivative of both sides, but now every time I take a derivative of y, I'm chaining on or multiplying on a y prime. So what I have is 3x squared plus 3y squared y prime minus, I'll distribute the 9 now, 9xy prime minus 9y. Well, I didn't state this yet, but we're trying to find the derivative. So that's the plan. Find the derivative of this function. Well, I didn't find the derivative yet. I have like a bunch of terms that some of them have the derivative in it, the derivative being y prime. What I need to do now is go algebraically solve for y prime. So I'm going to leave any term with a y prime in it on one side and take terms that don't have a y prime in it to the other side. And then how can I get this y prime by itself? Factor it out. And divide. And that's y prime. That's the derivative. I can reduce it by 3. I can take 3 out of top and bottom, but that's it. So one thing you can kind of tell is if I want to find like what the value of this slope is, I would need an x and a y to plug in. Because I'm going to have x's and y's in your answer, and that's fine. So it's fine to have x's and y's in your answer, it's just a little bit weird. Questions so far? Yeah.
So we've been using a chain rule this entire time.
Yeah, we just didn't know it. Yeah. Okay, so kind of to explain a little bit more, let's look at a really easy one. Let's look at x equals y squared. Now this is actually, it doesn't have to be an implicit function, or it's not a function, sorry, it's a relation. Because I could solve that for y, and y equals the square root of x plus or minus. But it's a little simpler like that, because it doesn't have the plus minus thing going on. What does that look like?
Sideways parabola.
Yeah, it's a sideways parabola. Okay, instead of y equals x squared, which is a regular parabola, x equals y squared is this. So there's points all along this thing, and let's say I wanted to find the slope. Let's say find the slope of the tangent line when x equals 1 and when x equals 0. Okay, so let's look at these two places. So when x equals 1, I'm here and I'm also here, so I should technically get 2 answers. And when x equals 0, I'm here. Any guesses for what this slope is going to be? I should have an undefined slope. So let's go see what happens. Okay, this function, or I'm sorry, this relation shouldn't be differentiable at x equals 0. We should get an undefined slope because it should be vertical. So let's say we take the derivative. The derivative of x is 1. The derivative of y squared is going to be 2y times y prime. So y prime is 1 over 2y. Make sense? So I didn't have to even get that complicated with it. Took the derivative. I don't have to factor out and stuff. It was just pretty easy. Y prime is 1 over 2y. So let's think about this. Well, what at x equals 1, what does y equal?
1.
1 or negative 1. When x equals 1, y equals positive or negative 1. Okay, because if I think about plugging in 1 for x and solving for y, I'm going to square root both sides and get a plus or a minus. When x equals 1, I could plug in 1 for y or negative 1 for y, and it would work. So I'm going to have two different slopes. So at x equals 1, here's my y values. The derivative then is going to be 1/2 and negative 1/2. That makes sense. I have two derivatives, two different derivatives when x equals 1, because this derivative is 1/2 and this derivative is negative 1/2. I used m to mean slope. And then at x equals 0, what's y in the original function? 0, right? At x equals 0, y is 0. I have a point here at 0, 0. So if I plug that in, y prime is 1 over 0, which is undefined. And that was good. Because at this point, at the origin, we said it looks like I have a vertical tangent line, so the derivative should be undefined. Kind of get it? Let's see if we do one more. Let's do one more hard one. Ooh, it's okay, so chain rule still applies. And it works like this. Derivative of the left-hand side, so derivative of 2y. Use normal rules. The derivative of this is 2 times y prime. The derivative of x squared is 2x. Now the derivative of the sine of y. Well, I'll get the sine happening to y, and then I've got y. So I'm going to use chain rule. I'm going to have the cosine of y times the derivative of y times y prime. Questions how I got that? Alright, finish it, see what you get. Because I'm wrong. Minus. Okay, sorry. 2x over 2 minus cosine y. Okay, question. Is this derivative ever going to be undefined? So, like, if they asked you, is this differentiable for all real numbers? You need to answer yes or no. Why no? Because cosine only goes up to 1. So for this to be undefined, this would have to equal 2. To be undefined, I'd need 0 in the denominator. To get 0 in the denominator, the cosine of y would have to be 2. But it's never going to happen because the cosine of a variable is always going to be between 1 and negative 1. So it's never going to be 2, so I'll never have an undefined derivative. Okay, there's just one more. this stuff also to find the second derivative, so we're going to find the second one. Remember, d squared y over dx squared is how they write the second derivative. If 2x to the third minus 3y squared. This isn't a great example because it's actually could be written explicitly, but then you'd have a plus minus and that would make it annoying. So take a second and find the first derivative. I think bring the 6x over, my 6's cancel, or 6x squared over, the negatives and the 6's cancel. Just for sake of time, I'm going to keep going. I can tell a couple of pieces aren't quite ready, but trust me that you get to here when you take the first derivative, okay, that you get to there. To take the second one, here's what I do. I take the derivative of both sides again. So the derivative of y prime is y double prime, or squared y over dx squared. These are the same thing. Okay, that's the same notation for second derivative. And now for x squared over y, what do you have to use? Quotient rule. So I got the bottom times the derivative of the top minus the top times the derivative of the bottom, which is going to be y prime, over the bottom squared. So the bottom is y, derivative of the top is x squared, the derivative of the bottom is y prime. Everyone with me so far? This is the second derivative, but you can't leave it that way. I don't really know why, I guess, but because I know what y prime is, I have to go back and plug y prime in for it. So this is the second derivative. I don't have to solve for anything else. But I got to go back here and replace y prime with x squared over y. And then, since we don't like fractions within fractions,
I love it.
you got to clean this up. But look how, this is what I would do. If I only have one term in the denominator, I can put this with it, and I can put this with it and make it a subtraction problem. So my answer would look like this. 2xy over y squared. Yes, I would reduce that, but hold on. And then I'd have x to the third over y to the third. Do you get that I'm allowed to do that? I can just pop this into this denominator and into this denominator. It's totally legal. So the y squared can go under here, and it goes under with this y, becomes y to the third. And that's legal. Oh, fourth, sorry. And I would reduce a y out of the first. So technically, I guess I'd have 2x over y. That's not a big deal. But what is a big deal is replacing the first derivative with what it is, and not leaving a fraction in a fraction. The homework tonight's a worksheet. Is anyone going to see the people who are absent to give this to them?